Thank you so much for the nice introduction. It's a pleasure to be here. I was actually a postdoc here a long time ago, from 2003 to 2006, so it's nice to come back and give a talk today. So I'll talk today about image domain transfer, which I'll introduce in a minute. So I'm part of NVIDIA Research. NVIDIA Research is a collection of researchers, and we work on a number of things, really all the way from sort of circuits, sort of very low level of hardware, all the way up to machine learning and computer vision. Our mission is to develop technology through research. We have about 140 researchers in 11 different time zones. And then my team, the learning and perception team, is about 20 people, and our focus really is a lot of computer vision research. And today I'll talk about some of it, and I called it image domain transfer. And the task I'm looking at is, one way to think about it is, can we teach machines some form of imagination abilities? And we'll see, it's not really imagination, it's just learning by example. But still, can we do things like this? Can we have an input image and ask a computer to translate into what it might look like, say, on a rainy day? Right? So given a sunny day image, can we teach it to take this image and translate it to look like as if it were taken during a rainy day? And we just need to apply some function f that takes this image and transfers it to a rainy day image. The question is, how can we do this? And I'll talk about a whole series of techniques that we've used to do things along those lines. Now, you might ask, why would I want to do this in the first place, right? So the example I showed is actually one I'll come back to. But there's other examples of translating one image to another with the goal of enhancing it or changing it in some particular way. So it could go low res to high res, for instance, or if you have a blurry image, you might want to make it sharp, or if you have a photograph, you might want to make it look like a painting, or if you have a low dynamic range image, you might want to make it look like a high dynamic range image, or if you have a synthetic image, you might make it look more real, or if you have a thermal image, maybe you want to add color to it. And then, so the other examples that I just showed, if you had a summer image, maybe you want to make it a rainy day image or a winter image. If you have a daytime image, can I make it a nighttime image, and so forth. So there's lots of application of translating one image to a different domain that's related but somewhat different. And being NVIDIA, the ones we're actually quite interested in is actually the last ones that I presented, so day to night, day to, or summer to winter, summer to rainy day. And the reason is, if you can do this type of translation, you might not need to acquire as much training data for a particular use case. Say you want to train, something for your self-driving car, right? And you've taken lots of footage in California, which is always sunny, right? So now I want to try and train it maybe, or test it on winter image. So either I go out and capture more data, or maybe I can take my existing data and make it look like as if it were winter or at night or rainy and so forth. So I'll talk about two main approaches, and I'll spend most of the time on the second part, or the second approach. So one approach is you take examples, and then based on this example, you derive how an image should be translated to another image, and this is usually called non-parametric, so we don't actually train anything, we really just base it on an example and take this example and somehow apply it to our image. So the function is, the translating function f takes an example in it and uses this to do the translation. And then I'll spend a lot of time on the learning-based methods where we have some training set and we learn this function f to go, say, from summer to winter. So how does this first one work? Well, it's often referred to as style transfer, and it's actually lots of old methods that do this, especially in graphics originally, but now also in the computer vision community, there's quite a few methods to do this. And the setup is usually as follows. You have some kind of content photo, right? It's usually a photograph. You want to take it and modify it to look like a given style photo. So I can give you a style and a content photo, and now you want to apply the style to the content and make it look like this, right? It's still the same pyramid or glass pyramid, and now it has the style of the architecture photograph on the left. So in a way, it's quite simple, right? We generate an output given the input and given the example, which is the style photo, and that's it. Now the question is, how do we do it? There is a lot of work on artistic style transfer, and you might have seen some of this, where the goal is to take a content and make it look like a painting, right? So here, we can apply the Starry Night and get output of, I think it's Tübingen, and now looks like the painting. What we want to look at today is what we call photo style transfer, where the input is a photo, the style is also a photo, and we want to apply this photographic style to our content image. And there's a slight difference between the two. In the artistic style transfer, you're okay, or actually you desire to change some of the geometry in the scene, right? So it's fine if the houses all of a sudden get bent a little bit, right? That's part of the style. Whereas for photographic images, that's not the case. You want to leave the geometry alone. You just want to have the look to be different. And the work we've done was just recently published at ECCV, and it's this two-step process. So we model this photographic style transfer as a closed form function, and we apply two functions. So it's function F1, function F2. The first function applies the style photograph, and that's a neural network based. And it does okay, but it leaves some artifacts. And then we apply sort of a second function, which we call, the first one we call stylization step, and the second one we call a smoothing step to get rid of some of the sort of wobbly artifacts that you can see. So how does this work? It's similar to a degree to the neural style transfer work that you might have seen. So the main insight is, or the main assumption that we make, and it turns out to be true, is that if you encode your image, so on the left side, it's the input image, and you have an encoder and encodes it into some space, and we just use VGG19, so we use an existing VGG network, we encode it up to the fourth layer, and take the features that come out of it. We make this assumption that the covariance matrix of those features actually encode the style somehow. So if you take the covariance matrix, HC are the features of the content image, so HC times HC transpose, is the covariance matrix, and we make the assumption that those somehow encode the style features. So we can take the features from both the content image as well as the style image, and now we're trying to enforce the covariances of the style features onto the content features so that they look alike. And it's actually fairly simple to do. So we encode the image, then we apply this whitening step. It's really like a normal whitening step. And then we apply a coloring step, which really just makes sure that those covariances are the same. And then we decode it again. So it's almost like a normal encoder-decoder architecture, except for this whitening coloring step, and out comes a style transferred image. And this is similar to previous work. We also make use of labels if they're available. Previous work also uses this, so if we know the sky, this part of an image is the sky, and this part of the style image is also sky, we map those together to make sure that we don't mix roads and skies and so forth. What you get is this. So style on the left, content in the middle, so we apply the style on the content, and we get the output on the right. And as you can see, for the top image, it looks all right. For the bottom image, it does apply the style of this image to this content photo. However, you can see in the clouds, there's sort of these artifacts, right? It's a little wobbly. It's sort of overall, yes, the style is there, but the geometry has suffered a bit, right? It's more wobbly than it should be. So we apply the second step, which we call photo smoothing. And it's actually a fairly simple idea. What we say is that the pixel in the resulting image, neighboring pixels, the relationship should be similar to the original image of the style. Sorry, of the content. They shouldn't change all that much, right? It's okay to apply the style, but the relationship between neighboring pixels should still remain the same. And we just impose this through an optimization, which actually has a closed form solution. So really make sure that the similarity between neighboring pixels is the same between the image that we are creating and the original one. And once you apply this, you get much better results. So this is the original output again, and once we apply this smoothing step, you get this. So all the wobbly artifacts, you can see they disappear, and it's much more similar to the original content photo, but it has the style from the style photo applied. So let me show you a few more examples and comparisons. So again, content and style, and we applied. Ours is on the right, and then in the middle is two previous methods. One is actually for artistic style transfer, and one is for photographic style transfer. And they work okay, but you can see, for instance, this one that was geared towards artistic style transfer, it often creates some artifacts, right? So the geometry of the pyramid is not quite the same anymore, whereas for ours, it remains the same. Let me show a few more examples. So again, style applied to the content photo, and this is compared to some older method, and this one is from last year, I think, or the previous year. And this is our result. And overall, ours works fairly consistently. The style is usually applied fairly well, and there's hardly any artifacts. I mean, you can see a little bit here that it looks a little, maybe not quite right, but overall it's very good. We did a user study to see what people thought about the different methods that I just showed. And we asked two questions to compare how well a photograph is stylized, so how well do we replicate the stylized photo, and how well, and how photorealistic is the resulting image. So basically, how little artifacts are there. And overall, ours was preferred. In addition, our method is actually fairly fast. It's very efficient. It's just really an encoder-decoder, which is fast to do. Right, so this is the first part I wanted to show. That's sort of a more classical method in a sense that it's based on an example, and you apply it to an image, so it's similar to older methods, except that it uses a neural network in the middle to do some of the work. Whereas all the work that I'm going to show from now on is all based on training on a training set and learning this function, and this function is represented as a neural network of some kind. And in particular, for all the work that I'm going to show from now on, it's all based on generative adversarial neural networks. You've probably seen GANs at some point in your course. I'll go over it very, very briefly. So a GAN is the following. So there's two components to a GAN. So you have a generator, which takes some vector z, it's a latent vector z, and based on this vector, it generates an output image. And at the beginning, it's just a neural network initialized with random weights, and it'll output some random image, right? And then there's a discriminator, which will check whether your output is realistic or not. And the question is, what does realistic mean? Well, actually what it means is the discriminator is supposed to check whether the synthesized image is similar, or the distribution of the synthesized images is similar to the distribution of your training data set. So you might have a training data set of, say, faces, as in this example here. Then the goal for the generator is to generate images of faces that are similar to the one in a training set and with a similar distribution. So that's its goal. And the discriminator's goal is to figure out whether the generator synthesizes images that are similar to those in the training set or if they're different. So, for instance, if the generator accidentally were to synthesize a car, it would say, no, it's not a face, or it's not a realistic face. Or if you were to generate, by accident, a cartoon face, it should also say, no, it's not a realistic face because it doesn't look like my training set of realistic faces. And you train these two in a ping-pong fashion, so both are neural networks, right? Both the generator and the discriminator are neural networks, and they're both trained together really well, one and the other, usually in a ping-pong fashion. And surprisingly, you can actually make this work, right? Even though neither the generator nor the discriminator actually knows anything at the beginning, they still manage to converge to a reasonable solution and synthesize realistic images. Most of the GAN work works in a supervised fashion, meaning you have training samples, training pairs, right? You have an input image, say a shoe given, an image given edges, and the output might be realistic looking shoes, right? It might be a training pair, so you know that you should go from this edge image to this particular shoe. We'll also talk a bit about the unsupervised setting, where I have two training sets, but they're not in correspondence. It might be one training set of daytime images. And the other training set might be nighttime images. They might all be driving videos, right? So they're related to training sets, but they're not identical in a sense that for X1, I have a corresponding image X2 that was taken at nighttime from the same point of view with the same cars in the same place, right? Because it's difficult to do, actually it's impossible to create data sets that are in full correspondence if you want to go from daytime to nighttime, right? Because there's always something that moves. So in your unsupervised fashion, I have just two separate training sets that are similar, but not in direct correspondence. In addition, we're also going to talk about unimodal versus multimodal. So what I just showed, or the original GAN that I just explained, there was a unimodal model, meaning if I want to do a translation, say from dogs to cats, it might only output one cat, right? Whereas a multimodal model, you might be able to give it sort of another style vector, and you might be able to go not just from one dog to one cat, but to potentially different cats that have different looks. So these are all the different ways of classifying the work that I'm going to present today. And there's lots of work in this space, and this is just a list of some of the GAN papers that came out over the last year or two. And I'll talk about some of our own work, and I'll put that in context. So the first one I'd like to talk about is Pix-to-Pix HD, which we presented last year at CVPR. And it's supervised, and it's multimodal. And really the goal was here to do a conditional GAN that goes from a label map, which I showed at the very beginning, to an image. So given labels of a scene, so the labels say, this is road, this is sidewalk, this is car, this is people, and so forth. Given these labels, I want to synthesize an image that looks realistic but corresponds to the label that I'm given. Right? So now I need to learn this somehow. How do I learn this? We will make use of GANs with a slight difference to the way I explained them at the beginning. So now the input is not just a latent vector, Z, but rather it's the label map, so it's an image. So we want to condition the generator on the label image. The discriminator still does the same thing. It still will tell you, or its task is to tell you whether the synthesized image looks like a real image, except it also knows what the labels look like, so it can sort of check whether, or it can try and figure out whether the synthesized image actually corresponds to the labels and whether it's similar to other images in the training set. Right, so in that sense, it's similar. In addition, what we do, we add sort of this multimodality to it. So we add to this additional step. So once we finish training, we look at all the features underneath a particular label. So we look at all the streets, we look at all the cars, and so forth. And then we try and cluster the features that we see during training. So for instance, for the road, you might have seen a lot of sort of standard tar, right? So standard roads. But you might also have seen cobblestone. And the hope is by clustering, you can figure out that there's sort of two dominant things, which is normal road, which is paved, and cobblestone road. Because once we do this, we can actually use this for the synthesis. We can give it to the decoder and say it should be one or the other. So you can actually do a multimodal synthesis. Then there's some other tricks that we play to make sure it actually works well, and those are really important. So if you just use a standard GAN, the quality of the results is usually okay, but not great. So we do two things. We change the generator and train it in a coarse-to-fine fashion. So we first train it to synthesize low-res images. And then once we're good at these low-resolution images, we take it and add sort of layers around it, sort of at the beginning and at the end, to make it synthesize higher resolution images, and that really helps a lot. Furthermore, we have these multi-scale discriminators, so we discriminate. So the discriminator not just looks at high resolution images, but images of different resolutions, which helps it to sort of have a better global view of what's going on. So it's better at discriminating badly synthesized images from what they actually should look like. And we also use this robust objective. So instead of just doing the GAN loss, we also add what people call a feature loss. So feature losses are often used when your task is to synthesize or create images of some kind, which means that you don't just look whether your synthesized image looks like a particular other image, so you don't just use an L2 difference, say, or an L1 norm between images, but rather you do it in the space of a neural network. So in this case, we take the features of the discriminator and check whether they're similar between our training images and our synthesized images, which also helps a lot. Sometimes it's also called a VGG loss, and it's quite useful. Right, so when you do all those things, you can do something like this. So here, label map is shown on the top. And then we go through different modalities. So it's always the same structure that we create, except we say, go through different pavements and through different cobblestone and change the cars, go through different potential cars. But always it does something sensible. If you look carefully, you can see that it's not always great. Like the white car, it doesn't look perfect, actually, if it comes up again. It looks slightly funky, but overall, it's actually surprising that you can learn from just a data set of label maps and their corresponding images, you can actually learn to synthesize realistic-looking, or mostly realistic-looking images. So here, we're going to now change some of the labels in the background. So some of the sky we make to, so here the sky becomes trees. Here, now we change trees to buildings and so forth. So you can actually change this on the fly. Not on the fly. You can actually change this and resynthesize, and you get a reasonable image out. It's really quite neat to do this. You can also, if you'd like, sort of paint parts that you want to be houses, or paint parts that you want to be a tree. So you can do modifications of your label map, and then the neural network just synthesizes an image according to your label map. So it's sort of painting by numbers, and it works fairly well. So in comparison to some of the previous work, so on the top left, it's a previous method that was called pix-to-pix. And then CRN, which is a more classical method in the top right. And then ours, the bottom two are ours, both with the feature loss and without the feature loss. And it's hard to tell, but the one on the right is slightly better than the one on the left. So this was pix-to-pix. Then more recently, we extended this to videos. So this was published at NeurIPS late last year. So now the difference is that we don't want to just take a single frame as input and synthesize an image, but rather a video of label maps and synthesize a video of realistic-looking scenes according to the video of label maps. Now, you could say, well, why don't you just use what you just presented, right, the pix-to-pix HD, and apply it on a per-frame basis? And you can do this, except it looks like this. Each frame is all right, except temporally they're not coherent because we didn't ask it to be temporally coherent. It doesn't know anything about previous images or next images that follow. So each image is okay, but overall, it flickers a lot, right? So it's not quite what you want. So we need to do something to make it temporally coherent. And it's fairly clear. Sorry. There we are. And it's really an extension of pix-to-pix HD, so it's very similar in sort of architecture. So the first thing we do, we build this sequential generator. So now we say you don't just get a single map as input, but you get multiple frames of label maps as input. You also get past images that we've synthesized to actually know what's happened before. Based on these, we create an intermediate output. In addition, we also compute optical flow between the previous images, so we know how things have been moving. We use the flow to warp the previous image into what the next image could look like, and then we combine our synthesized image with the warped image, what it might look like, into a final image, and that helps. And we always use a network to combine these. Then the trick of using multiple scales. For the discriminator, we use the same thing again. We do it not just spatially, but also temporally. So when we discriminate things, we look at different spatial resolutions, but also different temporal timeframes. So we look at larger distances as well as smaller distances. The training, we still do it progressive, but we don't just do it low resolution first, then high resolution, but we do it low resolution to high resolution, as well as temporally, we do it sort of smaller frames, smaller temporal time steps, and then larger ones. So we do it spatial temporally progressive, and then we alternate between space and time when we train. So if you combine all this, you can now take this video. Sorry, went too far. Take this video and turn it into a real video in a second. There we go. So you can see now it's temporally consistent. It is still not perfect. If you look carefully, you can see that some things are a little funky. The trees seem a little repetitive. The cars are glowing a little bit. But overall, yeah, it does. Let me play it again. Overall, it does a decent job. And this is running on unseen label maps, so it hasn't seen this particular sequence of label maps, of course. Right, and this is compared against the previous method, the Pixapix HD on the top right, previous method on the bottom left. That one was also not meant for temporal sequences, so it also flickers, and the hours on the right. It does actually do a surprisingly decent job at synthesizing people. Okay. Right. Now we can do the same thing for edges. So in this case, we trained it on edges and videos of people. Since we have this style, or this multimodality where we look at what things usually look like on average, so the clustering figured out there's different skin tones, and there's different hair colors, so now we can change skin tone and hair color. So input is just the edges on the bottom left, and we synthesize 3 different, the same person 3 times, but with different hair and skin tone. And here we've taken videos of someone dancing. So lots of examples of her dancing, and then we extracted the pose, and then from this pose we animated this little colored figure. And now we can take new poses and go from this little colored figure to her dancing again. And you can see, if you look careful, if you look careful, it works well-ish. There are some places where, some poses, maybe it's not seen during training, so it doesn't quite know how to do it right. The background wobbles sometimes a little bit. But, it's a start. Also, you notice that we use this colored figure, right? In previous label maps, they were all just uniformly colored, right? It just said, this is the label for trees, this is the label for cars, and so forth. Here, we did it slightly differently, and that improved results. So we have these different colors, and they're basically UV coordinates, like on a texture map, or like if you texture a person. That helps the neural network to know what's where, right? So you can figure out what hands are. It always knows which part of the hand you're looking at, and it's same thing for all other body parts, so that helps quite a bit.
This is the first time we combine machine learning and computer graphics to do.
I can't turn it off, no? Actually, I can. So let me do this, there we go. So this one was a demo that we did at NeurIPS. So this is actually running in real time. So we take as input a game engine that only outputs label maps. And then we take these label maps, and in real time, we translate them using the neural network. And we apply different styles, and this is just one example, just a short example that I found. So it's really doing graphics using the neural network. So all the textures and so forth, everything comes from the neural network. It only sees label maps that a game engine spits out. So the game engine is actually not used to produce graphics. It's only used to produce label maps. And you can take it and produce like a game looking, or something like a game. Right. Okay, so this was all supervised learning. So in this case, we always had input examples and what the output examples should look like. So we knew for this particular label map, this particular output would be desirable. So in this work, which is a bit older, we didn't use this. We tried to work with in the unsupervised case, where really we have these 2 different data sets, like the one on the left and the one on the right, that are separate. There's no one-to-one correspondence between them. They just happen to be similar, except one is at daytime and one is at nighttime. So now, how can we, given that there's no correspondence, right, how can we train a neural network to take an image taken during the day and output an image during the night that corresponds to it, but is at nighttime, right? So if we, let's say for a moment, all we do is we train again, and we tell it, here are my input images, right? Based on this input image, you have to synthesize an output image that looks similar to these other nighttime images. And that's all we tell it. Then what might happen is the following. The generator is going to generate things given the input image x1, but that are similar to the distribution of the nighttime images. However, it doesn't mean that there will be a correspondence between the synthesized nighttime image and the input image, right? I didn't tell it that they need to look alike. All I said is the nighttime images need to look like nighttime images, but I didn't say it needs to look like a nighttime image, but also like the original image, right? So what would happen is, given this daytime image, the network would probably just ignore this daytime image because it doesn't really need it to produce a nighttime image. It's just going to produce random nighttime images, which is not what we want, right? What we want is they should be in correspondence. So we make this assumption, which we call the shared latent space. So again, I want to create a nighttime image that actually corresponds to the daytime image, which is the case here, even though I've never seen them in correspondence. So I make this assumption that there's some space in which I can describe the scene I'm currently in, right? So if I take a point in this latent space, Z, I can somehow generate a daytime image as well as a nighttime image. And this latent space is sufficient to describe either one of them. But what I have then is different encoders that can go from a daytime image and encode it into this latent space. And they have different generators that can take a code from the latent space and generate either a daytime or a nighttime image. So if I want to translate it, then I can just use my encoder 1 to encode from a daytime to the latent space, and I can use my generator 2 to encode a nighttime image. But in addition, what we do is the following. We make, for these different encoders and generators, even though they're different ones, we share weights near the latent space. So the generator itself generates something and then encodes it to the latent space, and the generator takes it from the latent space and encodes it, and creates an image from it. And the layers that are near the latent space, we make them the same for all encoders and generators. And that in itself is sufficient to make sure that there is some similarity between the input and the output. So now what I can do is, I have the shared latent space, I can go between the different encoders. And the way you train it, there's one additional constraint that you know of, and that is if I encode an image and I decode it, so I take a nighttime image, I encode it with my encoder, and then I decode it again with my nighttime encoder, it should correspond to the original image, right? All I did is I went to the latent space, I'm going back to the same domain, I should be able to encode it correctly. And the same thing for the daytime image. And those constraints itself, they're sufficient to make this work. So now, here is input and output, again, trained in an unsupervised fashion, but it still manages to figure out that cars during the day, usually at night, they have their taillights on, the sky is black, the road is illuminated near myself, but then further away it might not be because my headlights might not go far enough. It also learns that sometimes, you can see here, that sometimes there's lights somewhere, so it sometimes just adds lights randomly in the sky, as it's learned that that's common. Also learned that the cars usually all look black or dark at night, whereas the taillights might be red or white. So this is going day to night. We can do the same thing for winter to summer. So in this case, we have driving videos of during the winter, driving videos in the summer, and it learns to go really from winter to summer, and it learns this on its own, and I'll show you some funky things that it's learned. So you'll see what it learns, that vertical structures are usually trees, right? But it doesn't really know that there's a difference between these electricity posts and trees. So sometimes it puts leaves on those because it looks a bit like a tree, right? So it thinks, well, the other things have leaves, so maybe they should have leaves as well, which is not a bad thing to think. Here again, you can see it put leaves on them. But it also learns that where there's snow in the winter, right, it should remove it. So it usually puts some dirt color there or some grass color, which is quite interesting. So it derives all this on its own, right? Nobody told it that these are trees and snow disappears in the summer. It learned that this is what usually happens. And this here goes from sunny to rainy. Again, it's learned that the sky is usually more gray when it rains. Usually there's reflections on the road, so it makes all roads slightly reflective. It also learned that things are slightly more hazy when it's raining, so it did that. It also learned that, which is actually interesting, that near taillights, there's often a red halo around them because of the mist, right? So you can see it makes those brighter. But then it doesn't really know to distinguish red car from taillight. So this red car now becomes, or has this slight glow around it because it also thinks it's like a taillight. Again, overall, given that it's only seen sort of separate data sets that are not in correspondence, it's managed to figure out that the road should be more shiny or more reflective, the sky should be more gray, and all of this was done automatically, right? Nobody told it that that's what it's going to be. So this was a unimodal translation, so you could only create one output, right? Not multiple different outputs. Then we have an extension of this work, which again is unsupervised, but it allows to output things in a multimodal fashion so you can change sort of the style of the output. And it works very similar to before. Again, we have an encoder that goes into some shared latent space, but and then you can come from this latent space and generate an output. In addition, though, we have these style encoders where we automatically try and learn what the style looks like of something that's being encoded. And when I decode it, I can give it a style, and the decoder should adhere to the style given. So it could be things like, I'm translating, say, leopards or lions, whatever it is, to cats. I can have different styles during the generation part, and the different styles correspond to different cats, but they're all cats in the same pose, just they're looking different. But overall, it's very similar to unit, except all this is the same, except there's this additional style encoder that we use. And we play the same trick that we played before, that if I encode something with a style and decode it with a style, with the same style, it should look the same. And again, that's sort of sufficient to make this all work. The structure is very similar to before, except now we use a bit more advanced network. We use residual blocks in our content encoder, which we didn't do before. For the style encoder, we use this trick which is called ADA-in, which is adaptive instance normalization. It's really where, for each layer, I enforce a particular mean and standard deviation, essentially. And that's sufficient to change the style. And it's been shown to work in a number of use cases. So what can I do with this? So in this case, we create a synthetic data set so we actually know what ground truth is, even though we learned it without correspondences. We actually have correspondences. So we have inputs of images of shoes, but only their edges. And we also have ground truth images for them, even though we trained it in an unsupervised fashion. And now I can ask it, the network, given this image of edges, give me example shoes, and I'll go through different styles. And it's going to give me shoes that all adhere to the edges, but of different colors, right? And they're sensible. So it's learned the sensible styles of shoes. Yes?
I'm sorry, I think I'm just a little confused, but can you talk a little bit more from the unsupervised case how you're doing this sort of mapping of the latent space without that seems to be non-obvious. That sort of seems like, how does this work?
Yes, it's not entirely obvious. So if you ignore the style for a moment, there's really only two constraints. One is that if I encode myself, right, and decode it myself again with the corresponding encoder decoder or encoder generator, then if I have a daytime image, I want the same daytime image back, right? That should work. And if I have a nighttime image, I should get the same nighttime image back. So that's the main constraint. In addition, when you think there's sort of encoder for daytime, encoder for nighttime images, generator for daytime image, generator for nighttime images. These are all neural networks, right? Each of them is a neural network. The neural networks, they share weights near the latent space. So it's the same, identical weights. So the encoders need to at the beginning of the encoders, they do something that's domain specific to daytime or nighttime, but then once they're sort of near the latent space, they have the same weights. So there's some kind of, we have forced them to be in a space that's similar. So at that point, it's independent if it's daytime or nighttime. And the same thing for the generator. At that point, at the beginning when they start generating things, it's the same weights either independent of daytime or nighttime. And then we have sort of the specific weights to daytime and to nighttime, which is the reason why they're in correspondence. And that's really the main reason.
So how are those shared weights determined?
They're trained.
Oh, you
Train. Yeah, but we train them, we just make sure, we force them to be the same during training. That's really the main insight. And yeah, it's the same here again, except with the addition of the style encoder. Right, so now, I can create all kinds of shoes. I can do the same thing for bags, and it learns the interesting styles, right? So you can translate this image of edges of a bag into various different bags. And now we can do the same thing that we did before. So let's start with the bottom one. We can go from summer to winter or winter to summer, except now, because it's seen lots of examples, right? It's seen some examples where there's more snow and less snow, some examples where there might be more leaves and less leaves. It actually learned to use these different styles. So now you can go from winter to summer, but also maybe to sort of a bit more spring where there's fewer leaves. And I can go from summer to winter, but with more or less snow, right? It's learned that mapping. Then we also did from cityscapes, which is realistic driving videos, to this synthetic images of driving. And it's learned that there's things like, I think this is rain, there's snow, and there's dusk. And the same thing, here we go from a synthetic to realistic images of city scenes, and it's learned that there's sort of cobblestone again and different pavements and so forth, different looks. And we can do the same thing for applying sort of photographic style in a way. So here we've given it lots of images of summer and winter images of Yosemite. But some of them were taken at night, some of them were taken at dawn, some of them were taken when it was nice out, some weren't. So it learns different styles. So when you go from summer to winter, yes, they all have a little bit of snow, but some of them are during a bright day, some of them are during the sunset, and so forth. And the same when you go from winter to summer. Some were taken at night, some were taken during the day, and it's learned that there's different styles. Now, the different styles, they're not disentangled, meaning I can't tell you it should be sort of nighttime and more snow, right? Because it doesn't know about this, so it's sort of one style which encodes all of the different aspects of the image, and you can't actually disentangle it. There's other work you could apply, but in this case, we didn't actually disentangle it. So now this is an example where we translate from a dog video to a cat video. But since we have a style code, we can go through different types of cats. And then we can animate the dog again. And all it's seen is really videos of, or images of dogs and images of cats. And it's learned how to translate them. And here we go, house cat to big cat, but we interpolate in the latent space. Sorry, we interpolate the style code. So it's the same cat you always see, or the same pose, I should say, but different types of cats. Go from cat to dog. Again, it's always the same pose, but different styles. And it's interesting, we've actually even learned that some animals or some styles have are furrier, so they're bigger, so it actually grows them a little bit to accommodate the fur and shrinks them again, which is quite interesting. And of course, once we have this, we can also do what's called style transfer, right? Meaning I want to apply a particular style given an example image, so similar to the very first part of the talk. So here I have these potential shoes I want to synthesize, given their edges. and now I can tell you I want this style, or this style, or this style, and I can apply it to all kinds of different shoes, right? So I can have the same style applied to different shoes, and the same thing can be done for, here we're going from big cats to house cats, and they can tell you, I want this particular type of cat, but in the pose of the big cat that's on the left. And again, this is in an unsupervised fashion, right? It learned what the correspondent should be. It learned that these poses are similar without being told explicitly. Right, so there's a comparison between sort of different methods. In all fairness, not all of them are actually geared towards this particular use case. So yeah, ours worked fairly well, which is not surprising, because we made it such that it would work well in this case, where some of the sort of more traditional neural art style transfer, they're not quite meant for it. This is actually the first work that I showed. It's not really meant for this case. So it doesn't work as well, because these are meant for sort of just applying style, but not changing to a particular animal, as we did in this case. Right. Okay. So this concludes my talk. So I've presented a lot of methods on translating one image to another image in various ways: supervised, unsupervised, unimodal, and multimodal. And that's it. Thank you.